welcome everyone to our December webinar. This month, we're going to go a little bit behind the scenes and talk about our AI, how it works, some of the applications we're using it for, and kind of what makes our analysis a little different than any other laboratory out there. So we'll give a few moments for everyone to jump in. About a minute before the 5 o'clock start time. So let everyone get settled, and we'll get started for the last webinar for 2020. It's now 5 o'clock. I'll give a few more moments for some more people to join us. As always, these are recorded and we post them on our website. Usually the following day, you'll get an email as well. So if you ever sign up and don't make it, don't worry, these are recorded and you can access them anytime you like on our website. And if you do sign up and don't make it, you get an email notifying you when the webinar is ready to go. So we'll just go ahead and jump right in. So the title of this webinar is Our Trusted AI, from Vet Clinics to Hospitals to Mold Analysis. So we're going to discuss a little bit just general information about Sporesight, who we are, how we use the AI, how the AI works, and some of the other applications our company uses AI in the veterinary and hospital space. And then at the end, there'll be a Q&A session. Feel free to write your questions in the chat during the presentation. We may stop and answer some of those questions along the way. We may also wait to answer them towards the end. So if you have any questions, you can put them in the chat, and yeah, we'll hope to answer anyone's questions. If you run out of time at the end and you have questions, you can always contact us. There'll be an email link, but you can also contact us through our website as well. So joining me today will be Shane Swenson. He's TechSight's CTO, Chief Technology Officer. He's a 25-year software industry veteran with development and leadership experience across a range of industries. He's been here at TechSight for 5 years. He loves working with high leverage technologies to solve hard problems and to make a positive difference in the world. And that's exactly what we do here at TechSight in Sporesight. He has a bachelor's and master's degree in computer science from MIT. And myself, I'm Dylan McIntosh, a certified industrial hygienist. Here at TechSight, I wear many hats. I'm primarily the product group manager for the Sporesight product. I oversee just about every little thing about this product. I'm our laboratory director, and I even do some analysis there on the samples themselves. So that's a little bit about us, who we are as an organization. Our company name is TechSight. We were founded in 2013. We're world leaders in machine learning and artificial intelligence, utilizing computer vision, digital microscopy. We create diagnostic testing for air, liquids, and smearables, as well as other things. We're used by labs, pathologists, doctors, vets, home and building inspectors across the country and across the globe. We have 3 verticals here at TechSight. Sporesight, who I'm representing here today, that's our environmental analysis side. Our mold air quality analysis, it's branded under the name Sporesight. And TechSight, that's our company name. It's also the branding for our human analysis. We have a collaboration with Mayo Clinic that we're very excited to work with them on many different tests. VetScan Imagist is our veterinary, our animal analysis, and that is in collaboration with Zoetis, one of the largest animal health companies on the globe. So a little bit about our laboratory. I'm the lab director. I'm the PAACV certified spore analyst. I'm a certified industrial hygienist. Our goal for now 2024 is working towards getting our AIHA MLab accreditation. We operate under a Texas mold analysis license. Texas is the only state in the country that requires the license, so that's why we don't have 49 other licenses as well. So we have, if you're new to Sporesight, we are a laboratory, but we're kind of in an innovative space. We're all about making home inspectors' lives better. Many laboratories out there, environmental laboratories, are focused more towards environmental professionals, industrial hygienists. There are only very few that are focused on the home inspector, and that's what we are. We're here to provide you with quick, accurate, and consistent and affordable testing for you and your clients. We really pride ourselves in having the best report that we deliver to our users. And we try to turn these things around as fast as possible, same day and next day report delivery. Coming back, we strive to have the best product. And for us, our product is the analysis, which we're going to get into with how AI makes our analysis better, as well as the report. Continuous innovation, we're always working towards making our service better. We're looking forward to releasing an app in the new year, a new pump in the new year, and as well as some other things that are coming, like some report updates and etc. Service is a key priority. If you're working with us, you probably have worked with some of our reps, Devin or Ellen. Probably get back to your emails and phone calls and texts really quickly, and that's kind of representing everything that we strive to be. So we're going to jump right into the first kind of section of our presentation of how we use AI here at Sporesight. So the general process is pretty straightforward. You, the home inspector, collect the slides, you run the sample, you take these little air cassettes and attach them to your pump, collect the debris onto the cassette, and then send them into us. And when we get them, what we do is we prep them, we apply some stain, we apply a cover slip, and we put it under a whole slide scanner like you see there. That digitizes the surface of the slide. We take a really high resolution microscopic image of what is on that slide. And then what happens next is that gets uploaded to our system, and that's where the actual analysis, the digital analysis happens. The artificial intelligence is run on that image to propose classifications on the objects that are on the slide. In this case, we're looking for mold spores and air quality contaminants like particulate matter. An analyst, after the AI is run on the software or on the scan, an analyst actually reviews the work that the AI did, makes some alterations and corrections, selects some images to include in the report that look good, and then we deliver the report to you. It's an abridged way, but that's how we use the AI. This is what our laboratory analysts see. Every other lab in the country will be having analysts look at these slides on a microscope and doing counting and identification on the microscope itself. We digitize the slides, so we present the analyst with digital images. It makes it much more comfortable for them, allows us to provide these really, really interesting photos in our reports. It also allows us to look at more of the slide than a typical laboratory. Most typical labs may look at 20 to 30, maybe 50% of a slide, and then extrapolate data out. At TechSight, we review the entire slide, and the analyst can do it much quicker and much more dependably than the typical method that the labs use. So from here, I'm going to turn it over to Shane to kind of give you a look into how our AI works, some of the things that we do to train the AI and how it actually works. I promise it's not going to be extremely technical, but it should be interesting to you in a number of ways. So I'll turn it over to Shane now to continue on.
Sounds good. So yeah, we're going to talk about some of the specifics for how we use computers to analyze these digital microscopy images and produce those proposed results that the technician can then review and generate a report from. And so, as Dylan said, we start with the prepared slide, and we showed that on the left here. And the first thing that we do with the digital slide scanner is take pictures of the area that contains the air sample itself and all the particulate matter that was captured. And the scanners take a series of pictures and then they stitch them together to form one larger image, and we upload that to our system. So the next image we're showing here is a zoomed out version of that uploaded image. That image is too large for single view to find everything we care about. And so we then subdivide it into a series of scenes, which are smaller images represented by the grid of green squares. And we process each of those scenes individually. And this is where we add the AI portion. We take each of those scenes and we apply our trained AI algorithm to identify in that scene the objects of interest and identify what type of object each of them are. And that is then what we use to propose the set of images for report generation. So we take the summary of all the objects found across all the scenes and combine them back together so that you have that 100% coverage in the report. Now, the key aspect to this is how do we produce an algorithm, which means a computer process that can take a picture like we've shown here in the middle and can find those specific examples of the things that matter. So in this case, we've highlighted a couple of Epicoccum, and there's lots of other things going on in that scene. And some of those are also important. And we didn't show everything in this example, but ideally we find everything on the whole slide that matters. And so the key to doing this is to have a very robust computer vision algorithm. And we'll talk a little bit about how we get there. And the technique we use is something called deep learning. And there are a few terms of art that we should talk about here. The first is AI, or artificial intelligence. And AI means using a machine, in this case a computer, to perform a task that represents or mimics human intelligence. And in this case, the task is finding and identifying the objects of interest in this slide images. And within artificial intelligence, there are a number of different methods. And the method that's important to us is something called machine learning. And the idea with machine learning is that we're going to use data to develop and improve our algorithm or improve the system. And then even within machine learning, there are a number of techniques. And the technique we're going to use specifically is called deep learning. And the idea with deep learning is we define a very flexible way for the computer to process the image. And then rather than trying to specify exactly how it should find and characterize the features of that image that matter, we simply show it lots of examples of the images that contain the objects of interest. And for each of those examples, we also check the answers that it gives. Specifically, did it find and classify the correct objects? And where it makes mistakes, we then make adjustments to the parameters in the model to make it do better next time. And you do this hundreds of thousands or millions of times, and each increment makes the model a little bit better until finally it's actually able to perform the task and reliably detect and identify the objects in the scene. And so that's the training process we show on the top. We start with that model architecture, which is really just a generic way of saying, take the inputs from the image on the left side and perform a series of processing steps to generate the output on the right side, which should be the predicted images. And we combine that with our training data set, which is that series of labeled images shown in the top center, to iteratively improve the model until we end up with the trained model in the top right. So that's the training process. Now that we have a trained model, we're able to apply what's called an inference process with it. And this is what we do in production with all of your air samples. We take that trained model, and now we take the scanned slide image, divide it into scenes. These are now what are called unlabeled images because we haven't told the model what's on them yet. The model processes each of those scenes, and it then produces the results. And then we take those results and collate them into the report. So the key in this process is that because we have a very generic model architecture, really all of the intelligence is developed through the data set that we use to train the model. And so the question is, where do you get your training data? And in the case of TechSight's history in developing SporeSight, we went straight to the experts. And so the picture on the top right is our CEO, Ben Cahoon, meeting with Dr. John Haynes, a mycologist in the state of New York, and essentially learning all about identifying and classifying mold spores. And so this is how we started our partnership and started to develop our data set. And then since then, we've continued to build that data set so that it is comprehensive and accurate in order to produce a model that will identify the things that matter and do so accurately. And so the goal of this process is to really build a data set that represents all of the common cases that matter, as well as the key corner cases or the difficult situations, so that that model will be robust and general as it's used to process new slides in the future. And if this is done properly, when we go through that training process, we should get a model that performs the task well. So in addition to the training data, we do build a couple other data sets. And the purpose of these other data sets is so that we can ensure that the model we're building works not just on the training data, but will work in a production environment as well. And so we have very strict rules about the separation of these data sets, because any slide that we use to train our model is going to essentially be now kind of, I guess you could say, tainted, as in the model will now know perhaps something about that slide and be able to give good answers on that slide in the future. So we separate our slides into the training data, and a subset of the training data is used during the training process itself to test how well the model is learning the task. And so this is called validation. We then have a distinct set of slides called holdout data, by which we mean these are slides that are held out of our training set. And when we train a new model, we then test it on the holdout data in order to see how well it's performing. And this allows us to iterate and improve our data set over time by training new models, testing them on the holdout, and then improving our training data set to perform better on the holdout in the future. Because we use the holdout so interactively, we then have a third category of data, which is even further removed from the model development process, called study data. And the purpose of this data is to really confirm that once we've developed a model, that it's going to perform in production at the level of accuracy that's required. And so this is data that represents usually multiple experts' assessments of a set of slides, and we look for concordance between those experts, and then we expect our trained model to perform within the bounds of that concordance. And this now tells us that we've captured the knowledge needed in our training set. We've then proven that it also will work in production through these studies. And so even though we train lots of candidate models, very few of them make it all the way through this process and are then deployed to production. So with a model that performs well, then the question is, why is the system itself accurate? And there are a few reasons for this. One of the keys is that these computer algorithms are very consistent once they've been trained. And because we can capture the whole air sample sort of debris trace on the slide in the scanned image, we can then apply the model to that entire image and count 100% of the objects on the slide, as opposed to a subset that would be needed just for human expediency in a manual review. We also, because it's a computer process, it doesn't get tired. It doesn't get hungry. It's very consistent from hour to hour, from day to day. And so the results show that consistency. And also, it turns out that when counting and classifying large numbers of objects in a population, this is a difficult task to accurately estimate relative ratios or total counts. And again, computers are very good at that type of task. If they have a large number of objects, of course, they can count them very accurately. So we find that these systems have the computer-based systems using our AI models have a much lower range of variance than experts or technicians do when they're performing this task manually. And then this isn't so much about accuracy, but there is an ergonomic benefit to these digital systems as well. And that is that by running the slide through the scanner and digitizing it, we can now display it on a computer screen, and we can set up a better ergonomic situation than trying to use a manual microscope all day for that reviewer. So next, let's talk just a little bit about some of the other use cases at TechSite. And again, Dylan mentioned that we've got the three verticals. We've got human diagnostics, veterinary diagnostics, and environmental quality. And we use the same techniques in all of these verticals. We use different data sets and of course, different trained models as a result, but the concepts carry over. And so we have a lot of practice in this in each of these verticals. In the veterinary space, we partnered with Zoetis, which used to be the Pfizer Animal Health division. And they've taken our product combined with a small slide scanner, and they branded that as their VetScan Imagist product, which is now their flagship digital diagnostics instrument. And together with Zoetis, we've deployed thousands of these scanners in veterinary clinics, and we're coming up on having scanned almost 3 million unique slides and processed those in our system. So we have a lot of experience there. And again, just as we've seen in environmental quality, we've seen that the accuracy of the diagnostics we're able to produce meets or exceeds that of human review. And then the next case for our system is human diagnostics. And here we partnered with Mayo Clinic. We're their preferred clinical pathology AI platform. We've also partnered with ARUP in Utah. It's a reference lab in Utah, and Quest Diagnostics. And again, as we test our systems with each of these partners, we find that they meet or usually exceed the diagnostic standard of manual microscopy. For example, we have a parasite detection algorithm that we found is 5 times more sensitive, meaning it'll find much rarer positive cases than the manual human review did. And in another example, we have a cervical cytology test that we ran it with a partner lab, not one of the ones listed here, but another partner lab gave us 300 negative slides that they had read, and we found 17 low-grade positives in that set. And again, this is just attributable to the total coverage and the consistency that the algorithm is able to apply in the image analysis. And so these same technologies that are helping in veterinary medicine and in human medicine are also helping to ensure we give you the most accurate and comprehensive report possible for your air quality samples. So with that, are there any questions? So Dylan, did you want to take this one or do you want me to?
Yeah, I can take this question. It's a great question from Robert. What does it do if we send in a new spore that it's never seen before? So this is a great question because mold spores are very they're very distinct. There's thousands and thousands of different mold spores out there. Our model's trained on 164 different classes of air quality particulate. So we don't possibly have every single type of mold spore covered in this. We've geared our model towards the most prevalent spores that are in the indoor environment as well as the outdoor environment. So every so often we do get one of these rare spores. part of our model development is building out an unidentified spore category. This is where we may train the model on some of these more rare spore types that we don't have enough to make a production level class with. So oftentimes it will get categorized as a unidentified spore. And then also, because we have the human and analyst do a read, what happens is we show our analyst more objects on purpose because we want to sometimes find some of these rare spore types that may get misclassified as a similar looking spore that we can then move into an unidentified spore. That's a great question. It doesn't happen very often. Our model is actually very robust. We have very good coverage in most scenarios, but every so often that does happen. And usually, if you ever look at our report, there's an unidentified spore category. Most often, if it does get classified as a spore class, it's there. If not, the analyst moves it there. So I've got another question from James. How accurate is our AI without human review, and how accurate is our AI with the human review? So since we designed the software to need a human review, I don't have good numbers to say how accurate it is without the review. As I just said, we purposely show our analysts results of lower confidence than we expect, so we can filter out the bad objects. This gives us better recall, gives us better sensitivity to finding more of these objects, and we do that because the human analyst is there. With our internal studies, the big improvement isn't necessarily in accuracy, but it's in repeatability. If you were to have two analysts look at the same slide following the typical laboratory method, where they look at maybe 30% of the trace, we've found that there's a variance of 44% between analysts on average. So that's a huge range of variability on a single test. Where our tests were much less variable, we actually get that down into something like 7% variability. Maybe let me look at the actual data here from that study. I was just looking at it earlier today. Yeah, so we go down from a 44% variability down to 15% between analysts using our system. And that, for as far as dependability goes, I think that is the bigger number. We find more objects using our system than the other system. It's around 10% or so on average on our internal studies, compared to the glass microscopist read. But where we really shine is the repeatability and the much lower variability between the analyses.
Maybe I'll take the next one. Travis asks, how is this AI different than something that you might have heard about in the news, like ChatGPT? And definitely, since it became kind of popular about a year ago, there's been a lot of public conversation about these large language models like ChatGPT and others. And there are a couple of key differences between our system and something like that. The first one is that our system, for the one we talked about today, is trained for one specific task, which is the detection and classification of air particulate particles. And whereas ChatGPT is based on a large language model, which is something called a foundational model, because it's trained to just be very good at language tasks in general. And one difference is it takes a lot more data to train a foundational model than it does to train a task-specific model, such as the SporeSight algorithm. It also means that when it comes to understanding the behavior of the SporeSight algorithm, it's a much more specific task, and thus it's easier to measure. And so there's another related question from Alex, which says, how do you know the AI won't make things up or make a mistake? And I'll talk about that in a couple of ways. So because our algorithm is really just detecting and identifying and classifying objects, we can test it very thoroughly. With a large language model, And then another thing to know about ChatGPT is it's called a generative model, which means it produces new content. So we produce, or our models produce identification of objects on the slide, but they're not generating images of those objects. They're not trying to generate other content, whereas the large language models do. And so the large language model has, like ChatGPT, has a very open-ended task, making it very hard to measure, very hard to test. There's lots of use cases to test. We have a narrower set of cases to test. It's still possible for the algorithm to make mistakes. So it can't really make something up because we've defined the set of outputs it can produce, which is, as Dylan said, a list of specific classes that we detect, but it can certainly make mistakes. And so we do test with that holdout data set and with our comparative study data sets to see that the overall performance of the algorithm is acceptable. And again, we don't need perfection here. We just need to be within the statistically valid range. And then with the analyst review, if the algorithm does make some mistakes, typically, if they're significant enough to affect the reporting, we'll catch those in the analyst review.
Yeah, that was great. We have time for one more question, so I'll answer this one really briefly from Benjamin. Will you use this AI to branch out to other areas like asbestos? Is that possible? It certainly would be possible. Anything that a human is looking through a microscope and using human judgment or training to identify objects under a microscope, and this goes beyond microscopy as well. There certainly could be a way to adapt an algorithm like ours we use here for air quality to identify that. There's a lot of other things that go into it beyond just can the AI do it to determine what sort of test we develop. But asbestos is certainly one that we've discussed internally, and there are some solutions on the market that use AI to do asbestos analysis. So it's certainly possible. Will we branch out and do asbestos? It's hard to say right now, but we're certainly always looking towards the future and to see what other tests we can grow the environmental side of TechSite. So with that, we'll close out. If any questions come up as you think about it, feel free to reach out to us. You can reach out to our sales team here, sales@sporesight.com. They'd be happy to answer any questions you might have or pass them along to someone who may. There's also an info form on our website that you can fill out if you want to go that way. Other than that, thank you for joining us for our December webinar. We'll be back in the new year. We intend to continue these on every month. So we look forward to hosting you again in the future. And as always, these will be posted on our website within a day or so after. So with that, have a good evening, and thanks for attending.